All right, so good morning. This is the first recorded episode of the Ronco Show in 2017. Yay! All right, so we've already dealt with differential equations. Now we're going to learn a technique to use on equations that are not separable. Okay, this is the next line of attack when you're looking at a differential equation. So for example, you should always attempt to separate your variables if possible, because separable equations are easy in comparison. Okay, this is when you just can't tease them apart. Okay, now you have some function of x and y dy and some function of x and y dx, and you can't tease them apart. Okay, you can't tease those x's and y's out. One thing that's important is that p and q are the same degree. Okay, so if one of them is an x squared, blah, 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 and the other one has to be also x squared or y squared of some degree, I mean, the exponents have to be the same on both sides, okay, or at least the largest exponent has to be the same on both sides, okay? So what we do in this scenario is we use a substitution. The substitution that we use is y equals vx. Okay, now, we're going to play around with this for just a second because we can turn the non-separable differential equation using this substitution. We can get it to be separable, just not of the same variables, and then solve it, and then undo the substitution. Okay? So, the process that this works with is this. So, if we just take this and we take a derivative on both sides, okay? So if we take we're going to wind up with, no, let's do this. d dx of y is equal to d dx vx. Okay, now by the way, v is some function of x. Okay, we don't know what v is, we just know that v is some function of x. And in fact, that means that when I take the derivative of the right-hand side, what I'm going to wind up with is the product rule. So we're going to wind up with derivative of the first, leave the second alone. Plus, leave the first guy alone, take the derivative. So writing it a little bit more compactly, now, one might say, really, really tempting at this moment to just turn that last dx over dx into a 1 and be happy and move on. But in fact, there's a nicer substitution that we're going to use. We're going to multiply everybody by dx, and we're going to wind up with a very nice thing like this. All right. Okay, so let's start with an example, because what we're going to want to do is we're going to want to use this in order to tease out all of our stuff. Okay, well, through an example, it'll be a heck of a lot easier to work with. So let's try this one. All right, so let's. And at first, like I say, you might attempt. You would attempt to use this formula, or this form, okay? So first, let's get things into a space that we're used to. So x squared dy is equal to xy minus y squared dx. Okay, so you see I took the first term, moved it over to the left, and then distributed that negative sign throughout. Okay? All right. Now, you'll notice that I can pull this x squared down into my denominator, But if I pull y out of this parentheses, I'm still left with a y on the inside. And that's where, the warning bell comes into play and say, look, I'm not going to be able to separate out all of the y's, okay? So this equation is not separable, okay? So what we do is we're going to, first of all, I like myself personally to, well, I like myself, but no, I like myself to get the dy alone if possible, okay? So I'm going to move the x squared underneath. All right. Now, let's go ahead and clean up the right-hand side a little bit. And get a little simplification. Okay, so here's where our substitution is going to come into play. All right, do you remember when we did integration by parts? And I'm sorry, not integration by parts. When we did U substitution, I said that you wanted to get all of your U's, get all of your X's into U's, DX's into DU's, right? You're trying to basically substitute out a variable. That's basically the principle here. But what we're going to get rid of is not the X, like it was back in U sub, but the Y. Okay, all of your Y terms are going to turn into V terms. Okay, now that's going to, scramble what you're looking at and turn it into a new form, and that new form is going to be separable. Okay, so for example, my y's in my numerator here are going to have to go, and this dy over on the left, that's going to have to go. But that's fine because we have a substitution for them both. One of the substitutions was the original, this guy. Okay. That's one substitution that's going to get rid of a v, get rid of a y. And the other substitution is for dy, and that's this guy. And that's going to get rid of that. Okay? So all of my y's get substituted first, and then my dy gets substituted also, and then we tease and play around, and then we get a separable thing. Does that make sense? Okay. So let's do that. Now, depending upon how comfortable you are, there are different ways of doing these substitutions that may make it a little easier or a little bit harder, whatever. One form that I like to recognize is this, that if y is equal to vx, then v is equal to y over x. Okay? It saves you a step of algebra, but all roads lead to the same solution. So we wind up with dy is equal to v minus v squared dx. Okay. And like I said, we have another substitution that we just brought up a minute ago that's going to deal with the left-hand side. So that becomes v dx plus x dv is equal to this. Okay. And when we rearrange this guy, we're basically now where we were last time, which is get all of your x's on one side, get all your v's on the other, integrate, and rock and roll. So I'm going to get my v's on the left, my x's on my right, and tease and play and all of that. So the v dx comes on over. Please try to only have one dx. I mean, it's got it, but to work with multiple dx's, but it just gets a little funkier. So let's pull out that GCD, try a little bit. We wind up with v minus v squared minus v dx, and of course we can simplify that to negative v squared dx and x dv. Now, this is clearly, we move all of our v's to the one side, we move all the x's to the other, integrate and play. So we have 1 all over v squared dv is equal to negative 1 over x dx. Integrate on both sides. So we have we wind up with v, ooh, that's weird, to the negative 1, negative is equal to, now we have a negative natural log of the absolute value of x plus c. And now we basically undo the substitution that we had before, okay? So we have negative v is equal to y over x, the negative 1 right there. We have the negatives. I'm just going to go ahead and knock out my negative signs if that's okay, so we don't really need them anymore. And we have the natural log, absolute value of x, plus c. Rearranging again. And now we solve for y. And we're done. Where? It was. They were both. Oh. So. Does that work? Okay. All right. So, how does this feel? Impossible? It's just a series of substitutions to make life a little easier. Okay? All right. So, let's try a couple examples. My page go. Sorry, let me use these. Okay. Let's do something along the methods of, okay. Okay. So again, you don't always know what you're dealing with each time. You know, attempt to separate by variables, but I'll tell you one thing, that when you start pluses all by itself, like added terms, subtracted terms, and you haven't even moved around your dx's and stuff, chances are you're not going to be able to separate. Okay, separation works really nicely if you can factor or divide out terms, but subtracting off terms doesn't work out so well because you wind up with that dx or dy on both sides. So it doesn't really play very nice, but it does work really nice if you're dealing, like I said, with factoring out, moving terms by division and multiplication, but not so much subtraction and addition. So we wind up with dy dx is equal to x minus y plus 3 all over 2x. Yeah, and you see right here, yeah, you can break up the numerator if you really wanted to, and y. And, that's fine and dandy, but, this, you see, once I move that dx over, it wraps everybody in a pair of parentheses. And getting the y by itself out and over to the left isn't going to be as easy as you think. So this doesn't play as nicely for separation of variables. Okay, no big deal. Let's just keep going with it. So what we can do is, again, like I said, throw the dx over onto the other side, and we wind up with and again, we're going to throw our substitutions at it. So x dv plus v dx. Get that left-hand substitution, get that in your head, because again, that's just nothing but the product rule. All right. You know, here you can see Vx all over 2x simplifies nicely. Now, don't think that you have to substitute for x. 3 over 2x is just fine all by itself. You're getting rid of y. You're not getting rid of x. So that third term, that 3 over 2x, is just by itself. All right. Get your x's on one side, your v's on the other, and let's roll. So here we go and do x, oops, excuse me. So we have x dv is equal to 1/2 minus v over 2 plus 3 all over 2x minus x dx. Oh, sorry, minus v. Okay. All right, so now we have how nice is this one going to play? So, my question is this going to be separable? Can we pull? Not going to be able to clean this guy up at all. This one does not fly. And let's go back to what I said before. Go back up here. Okay? This guy, your plus 3, that is not of the same degree as the other terms. This is not homogeneous. This will not work. Okay? Sorry to take you on a little wild goose chase, but the principle was still the same. Should have read the instructions a little better. Let's try one that is separable. Okay, this one works nicer because all of my terms will fly on this example. Let's go back here. And I'll write that in here. Okay, here all of my terms are of the same order. Agreed? Now this will work. So again, now we have, let's go ahead and do So let's clean this up. X dv plus v dx is equal to 1 over 2 minus v over 2 dx. Move the v dx over. Let's just go ahead. Oh, let's leave it alone. This one I think we could separate. I'm not a big fan of this book, but let's go through it anyway. Yeah, there we go. It comes out nicely. So we wind up with dv is equal to 1 minus 3v all over 2x dx. And you see it is separable. This is a U sub. And now cleaning this up a little bit, let's do now remember U we can substitute back out. And now when we jack an E under both sides, remember we don't want our answer in terms of V. We undo the substitution. And now we have we're going to have to clean this up a little bit further in order to get rid of the absolute bars, or we can put a domain restriction on it. But the fact of the matter is that we need to make sure that we can drop the bars. A lot of times you can kind of just get away by dropping the bars and then dealing with it later. I'll give you guys a second to catch up. We all caught up? Can I scroll down a little bit? Is that okay? to go from this line to this line, I put everything to the negative third power in order to get rid of the I negative, put everything to the negative 3 power, okay, in order to get rid of both sides. That's this. And we've seen that, did that last year and the year before. Natural log of u to the negative 1/3, this line. What I did was I got rid of the natural logs and right side into exponent form, jacked an e under both sides. Yeah, okay. So what's going on here is I'm stuffing an e under everybody, right? Okay. And I'm looking at these two right here. Well, the first e destroys that natural log, and I'm just left with this term. Okay? And then you can see I have the right-hand side here. And then I use my exponent rules to get rid of the plus c. E to the c is b, and e to the natural log cancels itself out, and you're just left with the square root of x. All right? Okay. Now, this particular problem is a little thorny, only because we have to make sure that we can drop the bars. So what we have to deal with is this. This must be greater than 0. Okay. So we can't even take the natural log of 0. We have to take the natural log of a positive. Okay. So this is our domain restriction. So moving things around, obviously x cannot equal 0, okay? And that's one restriction that we might want to just, okay, that we know that when we're dealing with this, we can't play around with x's that exceed that inequality. Okay? Y must be smaller than x over 3. Okay, now going back, as long as we have that domain restriction, we can drop the bar. Just writing this on your paper is kind of like saying, okay, we're fine now, drop the bars and proceed. Okay? So 1 minus 3y over x is equal to 1 all over b square root of x third. And of course, yes, you can go ahead and clean that up and put it to the rational exponents and all that good stuff. So we're going to multiply both sides by x and clean it up. Now, this is cubed. This is 3 over 2. Really hard. Yeah, because I just didn't want to deal with b cubed. Remember, it's a constant. As long as you realize that it's a constant, then you're fine. Okay, because a constant cubed is still a constant. They're just some, I don't really care what they are. But we need to say that they're constants. That was a heck of a lot. I mean, the differential equation, the actual solving of the equation, not that bad. It's the algebra mess to try and get y alone that can be the annoying drag of it all. Okay, it's just a lot of labor in order to get y alone. But if you were on an IB exam and all you did was the integration piece, you would get the lion's share of the work. Okay? Because, again, sometimes you can't get a nice closed form. This time I could, because all I had was a single y and it was not that bad. Okay? But, and I mean, it was lousy, but it wasn't impossible. Sometimes you can't get that closed form and you do want to leave it in implicit form. So sometimes it's not even worth the effort to try and rearrange this sucker so that y is all by itself. Okay? The only times that that might happen is if you need y later on down the road. Okay? All right. Let's try and do one that's not nearly as nasty. Not a big fan of this book, but we'll do others. All right. Clues that you're dealing with separable, okay, is if you have y over x or x over y already in your equation, other things, you know, that's kind of like screaming, hey, I'm separable. I mean, sorry, I'm not separable, I'm homogeneous, and I'm just going to do my substitution right away. Also, if we have stuff like, you know, where we have x's and y's and subtract rational function of some kind, that's kind of like saying, oh, hey, by the way, I'm gonna use my substitution. Okay, I'm homogeneous. All right, so let's like that. All right, this screams, hi, I'm homogeneous. Okay, you don't even want to try to separate that guy. All right, now notice that every one of those terms is of the same order. Okay, they're all the same highest squared and y, those together make an exponent of 3. So everybody is of the same order. Okay? So to the impossible? No. And now it's just a matter of cleaning stuff up. And you will notice that you will have a GCD of an x squared. Strike that, x cubed. Next. So let's get all my dx's over to the one side. So we're going to move this v dx term over to the left. We're going to have to get a common denominator and go from there. So we have x dv is equal to e plus 6v cubed 1 plus v squared minus v. All right. So yeah. On the left or on the right? Oh, this term that I just inserted? Okay. Going back up to here, I took him, moved him over, and since they're both dx terms, I can pull that v inside, right? It's basically like, what I'm doing is I have, we have stuff dx minus v dx, right? I get out of dx, so I get stuff minus v dx, and that's where I am here getting my common denominator. Okay, sure, no problem. And now you'll see that things clean up even nicer. And now rearranging to get all the v's in one side, all the x's on the other. Now, what are we going to do with the left? Yeah, definitely split it up, okay? Because we can't, a U sub wouldn't work nearly as nicely as we would hope because we still have the plus in there and it's just going to be gross. So break it up. And And the reason why I say stop right now is because you are not going to be able to tease that into a nice closed form. Okay, one of the things when I was taking calculus was I developed kind of a visceral fear of whenever I saw x's or variables of different sizes. Okay, and if I jack an e, well, first of all, I can't jack an e right away. I'd have to turn them into a single form. Okay, but you're not going to be able to tease that guy apart very nicely at all, if ever. Okay, simply because you're going to wind up with one x and y in an exponent and the other one not. Okay, and that's just going to be ugly as sin. Okay, so leave it alone. Yes, thank you. I lost an exponent. Good catch. Thank you. Done. Okay. All right. So I'm going to leave it there. We're going to go into some other questions real quick, but this episode of the Ronco Show has been brought to you by Homogeneous Differential Equations.